Welcome to Lecture 21, Taylor Series. So as motivation, recall from the previous lecture that we had a polynomial approximation of functions. So given a function f of x, think of this as like e to the x, we could approximate it using a degree n polynomial, Tn of x. So this is of course an extension of the linear approximation that you saw in first semester calculus. So the nth order approximation is a polynomial of degree n that approximates the function at a point x, and this is the formula that we had for that. So in this section what we're going to do is we're going to say, well, let's take the limit of this, and instead of having a degree n polynomial, let's let n go to infinity and get an infinite series. And that's going to be an approximation that's going to be better than any finite degree polynomial. So this is called a Taylor series. Remember that these were called Taylor polynomials. So replacing n with infinity makes it a Taylor series. We say that this is the series of f of x, or the series of a function, assuming that it converges to the function. A special case of this is when a equals 0, then the Taylor series is called a Maclaurin series. So the Maclaurin series is just a special case of a Taylor series. Okay, let's do an example. Actually, the remainder of the lecture we will spend doing examples, because that's the best way to learn this. So let's recall our formula that f of x is, I should probably call this k, not n. So the Taylor series is, I guess in this case the Maclaurin series, is the infinite series. So, I'm going to write it like this. It is the infinite series c to the k, x to the k, and we know what, and we have a formula for ck. So k equals 0 to infinity. Ck, it's the kth derivative of our function at 0 divided by k factorial times x to the k. Okay, so what's the kth derivative of the function? So if f of x is e to the x, then f prime of x is e to the x double prime is e to the x, and so forth. And the kth, every single derivative is just e to the x. So in this case, this is just equal to k equals 0 to infinity of e to the 0 over k factorial times x to the k. E to the 0, of course, is 1, so that's k from 0 up to infinity of x to the k over k factorial. So this is a function that is equal to e to the x. Well, at least somewhere. We're going to look at the radius of convergence next. So let's write this out. Let's write out the first few terms so we get an idea about this. For k equals 0, we have, so this is x to the 0 over 1. 0 factorial is 1. I'll write that as 0 factorial plus x to the first times 1 factorial plus x squared. I probably should have let myself more space for that. Let's change that. Plus x squared over 2 factorial plus x cubed over 3 factorial. And you see where this is going. Sometimes it helps to write out the first 5 terms or so in a series, because this is a nice compact notation, but often you don't quite see it in the same way when you see it written out like this. Okay, so this key point here, this infinite series is e to the x. Well, at least it's e to the x somewhere. So remember, this is a series centered at 0, and so there's going to be some interval around 0. Worst case scenario only at 0. Best case scenario everywhere, where this function, the series is going to converge to e to the x. And I'll give you the answer, or the spoiler right now is the radius of convergence, as we'll see, is going to be infinite. Meaning, if you plug in any, and I mean any real number, into this series for x, that series is going to converge to e to the x, to that number. Okay, so let me just ask, how do I want to do this? And let me say that, so the series is, I'll write it up here, k equals 0 to infinity of x to the k over k factorial. So let me ask, for which values of x does this series converge? And so to motivate this question, for example, let's recall, I could say, so let's suppose I had a function g of x, which was 1 over 1 minus x. And I said, what's the Taylor series of this? What's the Maclaurin series? And if you did this work, what you're going to get is, you're going to get that this is going to be equal to 1 plus x squared plus x cubed. You're going to get this. Or if you prefer, x to the n. I should say x to the k. So this is going to be the answer you get. But let me ask you this: this is the Taylor series of this function centered at 0. Does it converge everywhere? Of course not. If you plug in 1, you obviously don't get, or you plug in 2. 1. I'm not going to try because that's 1 over 0. But if you plug in 2 into this, you're clearly not going to get what happens g of 2. So though this is a Taylor series, it doesn't necessarily hold everywhere. In this case, it's only going to hold for this interval of convergence of radius 1. Okay, so for which values of x does this series converge? Does this series equal e to the x? So to do that, we're going to use the ratio test. So the ratio test, let's see if I have enough. Yeah, I'll do it right here. So let's take the limit as n goes to infinity of successive terms. So I think I called this c to the n plus 1 over c to the n as n goes to infinity of, so c to the n plus 1 is x to the k plus 1 over k plus 1 factorial, and the bottom is going to be x to the k over k factorial. And here I like to keep, as I learned last time, I like to keep the, I should make this, I switched from using n to using k. Let me go back and make that a k. Actually, it really doesn't matter. I'll just stick with k. Yeah, so it's nice to actually put the k in here because we have a k, but we also have an x, and we've got to be careful which one of these is going to infinity. Okay, so let's simplify this. This is the limit as k goes to infinity of, okay, so what do we have? We have x to the k, let's erase that little dot, x to the k plus 1 on top. We also have a k factorial on top, and on the bottom we have x to the k, and we have a k plus 1 factorial. Okay, so this is the limit as k goes to infinity of, let's see, so this part here just equal to x. And let's be careful with this part. That is, let me draw a little area. Remember what that is. That's going to be on the top, k minus 1, all the way down to 3 to 2 to 1. That's on the top, and on the bottom that's going to be k plus 1 times k all the way to 3 times 2 times 1. So each one of these is going to cancel with that, and we're going to get 1 over k plus 1. So this is the value of x times 1 over k plus 1. So x is some finite number. That's some number. And we're dividing it by something that gets larger and larger. So I can write this as some number x times, that's not changing, times the limit as k goes to infinity, 1 over k plus 1, and that's equal to something finite over something huge, so that's going to be equal to 0. So this tells us that our series converges for all x. So in other words, the radius of convergence is infinite. So what that means is that e to the x equals this infinite series, x to the k over k factorial, and for all x. And that's key, because that's different from the example that we've seen with this geometric series. Okay. Next, find the Maclaurin series, again, Taylor series centered at 0, of cosine of x. So it's the same formula involving the derivative. So let's compute a few derivatives first. Notice that f prime of x, the derivative of cosine, is negative sine. The second derivative is negative cosine. The third derivative is positive sine. And the fourth derivative of x, it's supposed to be a 4 in there, is cosine again. And then this thing repeats. So this is I'm going to say cycle, I can write that better, I can improve that. So this is a cycle of length 4. And okay, so really all that we're worried about are actually these values evaluated at 0. So how do I want to say this? Let's do this. So this is, so f prime of 0 is 0. F double prime of 0 is negative cosine of 0. So negative 1. F triple prime of 0 is sine of 0 is 0. And the fourth derivative, 0 is cosine of 0, which is 1. So this sequence of derivatives is going to alternate. Well, I guess the 0th term is going to be 1, 0, negative 1, 0, 1, 0, negative 1, 0. And you should see this and so forth. So notice that this repeats with a cycle of length 4. Okay, so our series is going to be the infinite sum of k equals 0 to infinity of the kth derivative over k factorial. So it's the same thing we've seen before. So now I'm going to write this out. So let's see. So before, the last problem, what I did is I had a nice formula for the kth derivative. It was e to the x. Plug in 0, it's 1. So the last problem, I took this formula and I looked at this top thing and I said that's equal to 1. So I just replaced it with 1 and I was done. Now it's not quite so simple. This thing is going to sometimes be 0 or 1 or -1 or and it's going to have this period length 4. So there's not really a good way, at least I can't see right now, a good way to just replace this with a simple formula. So instead I'm going to write out the first 6 terms or something. So the k equals 0 term is going to be, let's see, the k equals 0 term is going to be 1 over 0 factorial times x to the 0. So that's going to be 1. The next term is the k equals 1 term. That's 0x over 1 factorial. The next term, next we have we have 1/2 over 2 factorial. So let's see, that's be minus 1 over 2 factorial x squared. Then we have plus 0 over 3 factorial x cubed minus, no, it's plus 1 over 4 factorial times x to the 4th. Let me keep going with this. Minus, so plus 0 over 5 factorial, x to the 5th, and I think I have room for one more, minus 1 over 6 factorial, x to the 6th, and then we have this plus or minus, and it just goes on like this. So there's clearly something repeating here. Hopefully you can see the pattern. On top it's 1, 0, -1, 0, 1, 0, -1, 0. And so in the end, we lose all of the odd degree terms. And so let me write this as 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial plus x to the 8th over 8 factorial plus minus plus minus. Yeah, let me actually do one more just for balance sake. Minus x to the 10th over 10 factorial. And so hopefully you should see this pattern. Now, is there a good way to write this as a closed formula? Well, there actually is. And it's not obvious. The first time you see this, it's not something I would expect you to see right away, but let me show you how to do it and then see if you can pick out how this works. So I'm going to write this I'm only getting even powers of x. So I'm going to write this as a fraction on top. I'm going to put x to the 2n. Notice by doing that, as n increases, I'm missing all of the odd powers. So let's take a term. This is 2n. So that on the bottom is also 2n. So on the bottom I have 2n factorial. What do I have now? What about the signs, SIGNs? So I have plus, minus, etc. What's going on? Well, I'm going to write that as -1 to the n. Is that right? Or it should be n plus 1. So if n equals 0, that will be a positive. If n equals 1, that's a negative. Okay, good. N equals 2, I get this term, and that's positive. So there it is. This is the series for cosine to the x. Now we still have to ask when it converges. Let me clear that screen. And let me rewrite the I think that was n or k. I think I'll use n. So cosine is the series -1 to the n times x to the 2n over 2n factorial. So we know this thing converges it converges at 0, because if you plug in 0, you get just a constant term, which we said was 1. And it might converge to some interval around 0. We want to know how big. And spoiler alert, like e to the x, it's going to converge everywhere. R will be equal to infinity. So to find R, we get the ratio test. So the ratio test, we take the limit as n goes to infinity of c to the n plus 1 over c to the n plus 1. Ooh, okay, so we need to take the limit of the ratio of successive terms, and in this case, we have to take successive terms including x to the 2n. So of this entire, so I should probably write x to the so I should probably just to be clear, specify that I am including the x's. Okay, so this is the limit. This might get a little bit messy. So n goes to infinity of, okay, negative 1 to the n plus 1, x to the 2n plus 2 over 2n plus 2 factorial. So 2n plus 1 is 2n plus 2. On the bottom of this, we're going to get negative 1 to the n. We're going to get an x to the 2n, and we're going to get 2n quantity factorial. Okay, let's simplify. These negative, so that whole thing is equal to negative 1. It's just 1 over negative 1, or maybe vice versa. Doesn't affect the absolute value, so we can ignore it. How else can we simplify this? The limit as n goes to infinity of, so we have x to the 2n plus 2, so that's x, let's see, x to the 2n times x squared, correct? Yeah. And on the top we have 2n factorial. Now on the bottom we have x to the 2n, and 2n plus 2 factorial I'm going to write as 2n plus 2, I have room for this, 2n plus 1 times 2n factorial. Okay with that? That's 2n factorial. So let's cancel. Those things are going to cancel. Those things are going to cancel. And we get the limit as n goes to infinity of x squared over 2n plus 2, 2n plus 1. Okay, so this guy it's a number. It could be huge, it could be millions or billions, but it's constant. It's not changing. That's fixed. This is getting larger and larger and larger as n goes to infinity, so this limit is going to be equal to 0. And 0 being less than 1 means that this series converges for all x. So let me say that this, I'll put this for all x. So instead of rewriting it at the bottom like I did the last time, cosine of x, if you take any x, any real number, and you plug it into this infinite series for x, the thing that series will converge to some number, and that number is exactly cosine of x. And if you step back and think about it, that's pretty incredible. That for every single point, every single real number x, we can write cosine of x as an infinite series that doesn't equal, but converges to that number. Let's do another example. This one is a little more complicated. Find this Maclaurin series of x cosine of x. So one way to do this, using our formula, is to take the derivative of this and take the second derivative and the third and so forth. And as you see, this is going to get messy really quickly because these derivatives are going to involve product rules, and it's not even clear that there's a nice closed simple formula for the kth derivative. So here's a better way. So recall that cosine, I'm going to squeeze this in here, cosine of x is 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial plus x to the 8th over 8 factorial minus x to the 10th over 10 factorial plus and minus and so forth. And this has a nice closed form, as we saw, of n equals 0 to infinity of negative 1 to the n times x to the 2n over 2n factorial. Sometimes it's nice to look at a simple closed form like this. It's nice and compact. Other times it's nice to actually look at all the series. It's more familiar. It looks more like a polynomial that just goes on forever. Okay, so to find the Maclaurin series of this, all you do is you just multiply every term of this by x, and you're done. So you can, if you want to, you can rewrite this and just increase all of these exponents by 1 and make that an x. Or you can just stick on an x here, x to the 2n plus 1. So let me do that latter one. So this is n equals 0 to infinity of negative 1 to the n times x to the 2n plus 1 over 2n factorial. There we go. And if you want to, here I can say this is x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial, then plus minus, and I'm just going to leave it like this. And this thing converges everywhere. Instead of saying converges everywhere, I'm just going to say that this holds for all x. And it holds for all x because this converged for all x. So if this converged for all x, multiplying by x is not going to change the convergence as well. And actually, I have some room here, and I wasn't going to do it originally, but I can squeeze in this example, and I think it's appropriate. Actually, I think it's a good one too. So let me call it example 3.5, because I think I have an example 4 in the next slide. Find the Maclaurin series of sine. So one way to do this is exactly how we did it for cosine before. We just compute successive derivatives and plug in 0, and you get this cycle of period 4, sine, cosine, negative cosine. Plug in 0, you get the cycle involving 1s and 0s, negative 1s, and it will work. But there's a better way. And it all comes down from the fact that we already have the series for cosine, and the theme of this slide is computing new Taylor series from old ones. So this is what cosine is, and we take the derivative of cosine, we'll get negative sine. And so the derivative of this power series is going to be negative the derivative of the power series, or the Maclaurin series for sine. Okay, so let's do this. d dx of cosine of x equals negative sine of x. So let's compute this term by term. Derivative of the first term is 0, so 0. The next one is minus 2x over 2 factorial plus 4x cubed. That should be a cubed. Try that again. 4x cubed over 4 factorial, or plus, minus 6x to the 5th over 6 factorial plus 8x to the 7th over 8 factorial minus 10x to the 9th over 10 factorial plus minus so forth. Okay, so this thing here is negative sine of x. Let me factor out a negative sign. So this is negative. So, before I simplify, let me notice. Let's see what happens here. Notice if I take 8 factorial so 8 factorial is on the bottom. So the bottom is 1 times 2 times 3 times 4 all the way up to 8, and I multiply by 8 on the others. The 8s are going to cancel. So just in general, notice that n factorial over n is 1 over, or n over n factorial is 1 over n minus 1 factorial. Okay, so this is going to be, I'm going to pull out the negative sign and I get x over 1 factorial minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial plus x to the 9th over 9 factorial. I'll do one more for good measure. Minus x to the 11th over 11 factorial and plus minus and so forth. And now we can actually write this in closed form. We can say this is n equals 1. Ooh, hold on, or 0. Let me delete that, and I'm going to fill that in later because I'm not actually sure. Okay, so look at this and I say we want to pick off the, how do I want to say this? So negative sign is negative times this. So let me stick let me make that negative sign in red, and I'll put the negative sign here in red as well. Just so the part in black is sine. So this here is sine of x. So that's the answer that we're looking for. Okay, so we want a closed formula for this, and so we're only picking off the odd powers of x. So I'm going to put a fraction here. I'm going to put a x to the 2n plus 1. And now, if I do that, notice I'm going to only pick off the odd powers. And this 2n plus 1, that is equal to whatever odd number this is, which is the same as the thing down here. So I better put a 2n plus 1 factorial on the bottom, and then here's this alternating sign business. What happens here? Negative 1 to the n, or is it n plus 1? I think n is correct. Yeah, you can check that. So let me do the same thing. Let me circle this in blue, and I'm swiftly avoiding that red negative sign. That's equal to sine. And this converges for all x. Now, let me do this one more way. I said at the beginning, you can take the derivative of this, or you can take the derivative of that. Let's take the derivative of that, and let's see what you get. And see if you get the same thing. And you should, but, well, let's check. So sine of x is also equal to, let's see, so sine of x, okay, so the derivative of this is negative sine of x. So sine of x should be negative times the derivative of that. Okay, so sine of x is negative times dx of n equals 0 to infinity of negative 1 to the n, x to the 2n over 2n factorial. Okay, so I'm just going to skip a step here. I'm going to just bring in the derivative sign into the inside and take the derivative of each term. It's not completely obvious. You can do that with an infinite series. It works with a finite series, but if you want to know the details, take Math 454. It's a great class. You'll see that and a lot more. Okay, so this is negative times n equals 0 to infinity of negative 1 to the n, 2n x to the 2n minus 1 over 2n factorial. Okay, now let me do two things. This 2n is going to cancel with the first term in the 2n factorial, leaving me with a 2n minus 1 factorial on the bottom. That's the first thing. And the second thing is that this negative sign I'm going to bring inside and put, so here I have n copies of negative 1. If I bring this in, I'll have n minus 1 copies of negative 1. So this is n minus 1 or n plus 1. Doesn't matter. So this is n equals 0 up to infinity of negative 1 to the n minus 1 or n plus 1. Doesn't matter. I'll do n plus 1. I'll do n minus 1 because I can always make a negative sign into a positive sign pretty easy. Times x to the 2n minus 1 on top, and on the bottom is going to be 2n minus 1 factorial because this is canceling with the first term of that. So notice, this is my answer. This is sine of x. Several comments. Why is this different than that? Well, are they? They look different. But convince yourself. Oh, I realize I forgot to put my 0 in the bottom of that. Right down here. Starts at 0. These things I claim are actually... Ooh, hold on. So I started at n equals 0 because my first term should be x to the 2 times 0 plus 1. What did I do down here? Down here, my first term, x to the 2n minus 1, n should be equal to 1. So n equals 1 is the smallest term, so I should actually probably I should start that at 1. Why? Did I cheat? No. So we have a formula for the derivative of this term by term. That formula really only works if n is not 0. Because if n is, if n equals 0, what's negative 1 factorial? That doesn't make sense. And if n equals 0, we can ignore that anyways because the n equals 0 term is just a constant. When we take the derivative of that, we get 0. So there's nothing wrong. You can't stop me from starting this series at n equals 1 and ignoring that constant term because I'm taking the derivative of it anyways. So let's make that n equals 1 and make that n equals 1. So notice, even though these two series look superficially different, convince yourself that they both describe this series right here. Both. It's a good time to pause the video and check by hand right out of the first 5 terms of this, right out the first 5 terms of this. Convince yourself they are both this series right there. Okay, now for the last problem, as I promised. This one looks like a step up. Evaluate this integral. Now, this is something where, as far as I know, we can't do this without using Taylor series. I don't know how to evaluate something like x cosine x cubed. Maybe there's a weird u substitution trick, but I doubt it. But what we can do is we can, so what is cosine of x cubed? What we can do is, in place of x right here, instead of having an x, we could stick in an x cubed. Let me write, plug in x cubed for x. I don't want to say that's equal to x, because that's not, but let's, so cosine of something is equal to this creature, where that something is raised to the 2n. So cosine of x cubed is this creature, where that's x cubed raised to the 2n. Oh, and then we got to multiply by x as well. Okay, so let's write that down. So so before we go any further with the integral, x cosine of x cubed is x times n equals 0 to infinity of negative 1 to the n, x cubed to the 2n over 2n factorial. Okay, this is, let's do two steps at once. This guy is x to the 6n, and then I have an extra x coming out there. So this is going to be negative 1 to the n, that doesn't change, x to the 6n plus 1 over 2n, I should probably put this in parentheses, factorial. Okay, so this integral is the integral of n equals 0 to infinity of negative 1 to the n, x to the 6n plus 1 over 2n factorial. Now we can just, this thing is this thing is an infinite series, so we're integrating this as an infinite polynomial, so we can bring the integral inside and integrate each thing term by term. Now, again, if you want to know why I can necessarily do that, it actually does take, you know, some serious math to verify that, and that is also done in Math 454, Advanced Calculus 2, or Real Analysis. So, okay, so this is the infinite sum. There are some subtle cases when you actually cannot swap the order of the sum and an integral like this, but that's way beyond the scope of this class. So let's integrate term by term. X to the 6n plus 1. I can, let me fix that. X to the 6n plus 1 over 2n factorial. And so so this is the infinite sum, n equals 0 to infinity of, okay, let's see, negative 1 to the n, that's a constant. 2n factorial, that's also a constant. Then we have x to the 6n plus 2 over 6n plus 2. Now let's not forget our plus c. So this is the value of the indefinite integral. And this thing converges everywhere for all x, since the original series does. Okay, so oh, actually, yeah, we have evaluate this from 0 to 1, because, okay, so let's suppose we didn't have these limits. What does this tell us? Well, can we write this in terms of sines and cosines? I don't know. I really don't know. Probably not. Well, Probably is a way, but it's probably in no way obvious how to do it. But this is still something, this is a function. It holds for all x. You can plug it into a computer. This is a perfectly good answer, and you can, use your Taylor's series or your Taylor's theorem for the remainder to get as much precision as you want. But in this case, we actually want to evaluate this integral from 0 to 1. And this is really cool because we're going to get an exact answer here. And for an exact answer of a definite integral for something that we do not know a closed form solution of in terms of trig functions. Okay, so let's continue. I ran out of room, so I just cleared this. Okay, so this definite integral is n equals 0 to infinity of negative 1 to the n over 2n factorial times x to the 6n plus 2 over 6n plus 2. So this was the indefinite integral, and we want to evaluate this from 0 to 1. Okay, so this is the great thing about this is we can just plug in these two values. Let's see what happens when you plug in. So when you plug in 0, this entire thing is going to go away, right? Oh, is that true? Yeah, the smallest term is x to the 2, yeah. So this is going to be n equals, I'm actually not sure where this is going to go. Let's see. This may not actually help us. 2n, I mean, we might get an expression, but I don't know what it's going to be equal to. Let's see. 6n plus 2. On the top we have negative 1 to the n. That's when I plugged in 1. And of course I can plug in 1 to this. That goes away, or it becomes 1, I should say. And then I'm going to plug in 0. Okay, so this, well, let's see. So, yeah, I don't know a good way to write this. But let's write the first couple terms. Let's approximate it. So this thing is, so for n equals 0, we have 1, we have 1, and in the bottom we have, wait, is that right? Yeah, on the bottom we have 2. Let me put parentheses over here just to clarify that. So the n equals 0 term, that this is 1/2. The n equals 2 term, or n equals 1 term, so there's a negative sign, and then on the bottom we have a 2 here, and we have an 8 here. So we have a 2. That's not my pen. We have a 2 times an 8. N equals 3 term. We have a 1 on positive 1. On the bottom we have 3 factorial. That's 24. And then we have 6 times 3, 18, plus 2 is, 6 times, where was I? N equals 0, n equals, this is n equals 0, n equals 1, n equals 2. Okay, yeah, so n equals 2, that's going to be 14. 6 times 2 plus 2 is 14. Let's put parentheses here so we can see them easier. The n equals 3 term, let's also do the n equals 4 term. So the n equals 3 term is going to be minus 1 over 6 factorial, that's 720, times n equals 3, 18 plus 2 is 20. And then the last term is 1 over 8 factorial. Let me type into my computer what that is. Okay, that's 4320 times n equals 4. 6 times 4 is 24 plus 2 is 26. And you could see this number is getting small really quickly. So if you add these things up, actually this one I did in advance, didn't do the intermediate steps though, this is equal to 0.4398. So, okay, this integral is not equal to that because I made an approximation sign here. So I said approximate. This is the first. You could say 5 terms, or you can say up to the term that has the 8 factorial in it. So really, it's like the first 8 or 9 terms, and because I'm skipping every other term. It gets to the 8th degree term. Okay, so our answer, this thing here, is approximately equal to 0.4398. How good of an approximation is this? So, what error did we commit? Now we don't know the exact error, because if we knew the exact error, we could just add or subtract it to that and we would have our final exact answer. But we can bound it. So recall by the alternating series remainder test, or theorem I should say, by the alternating series remainder theorem says that the error, if you truncate this alternating series at any point, then the error, in other words, the total sum of the tail, everything that comes after it, things we threw away, is no bigger than the very next term. So the alternating series remainder theorem says that the remainder is no bigger than the very next term. So this is the very next term. This is the positive value for this. So we're ignoring the negative one, the possible negative sign. Okay, so what's the next term in this series? So R5 is less than or equal to, in this case, B6, which is 1 over 10 factorial. Now that's 32. Now this number is really tiny, and actually this one I did in advance as well because I knew I would not do it on the fly or in my head. So this is 8.61 times 10 to the negative 9th, and this is tiny. So this answer that we got here is so this approximation is good to, it is within this, which is practically 10 to the negative, almost 10 to the negative 10th of the actual value of this interval.